Hello everyone, I welcome you all in this lecture. Today we will discuss some concepts that are essential to supervised learning algorithms. They affect the performance of the learning models and hence taking care of them is very crucial. Let's start. So as a recap, so far we have discussed many supervised learning algorithms. We discussed linear regression, we discussed k-nearest neighbor algorithm, we also discussed decision tree, logistic regression, and in the last lecture, we also discussed artificial neural networks. In today's lecture, we will try to cover these topics. We will see what is the difference between parameters and hyperparameters. We'll also discuss a very important concept of underfitting and overfitting, which leads to the next topic, that is regularization. We will also discuss the concept of validation set. Let's discuss them one by one. First, we will start with what do we mean by learning models, because we have seen this term many times now. So we often use learning model and learning algorithms interchangeably. However, in machine learning, different models can mean two things: using distinct learning algorithms or employing the same algorithm but with different hyperparameter values. For example, we can have models ranging from logistic regression to artificial neural networks with different learning rates, and even linear regression models with simple to complex equations. Each choice here represents a unique way to learn from data and hence referred as a unique model. So when we use the term learning model, it might refer to different algorithms, or it might also refer to the same algorithm but different hyperparameter values. So in this specific case, you can see that logistic regression is one algorithm, decision tree is another algorithm, neural network with a specific learning rate is one model, and neural network with a different learning rate is a different model. So all of them are called different learning models. Now let's talk about another very important concept called loss function. Loss function, also called cost or error function, they are fundamental in measuring how well our model predicts the desired outcome. The goal in machine learning is to minimize this specific function, thereby enhancing the model's accuracy. For instance, in regression tasks, we often use mean squared error or MSE, and for binary classification tasks, we use binary cross entropy as a common loss function. These functions guide our models to learn from their errors and help us gradually improve the predictions. A good loss function in machine learning should have several qualities to be effective, such as it should be differentiable and it should be convex in nature. Here, differentiability refers to the fact that loss function should be differentiable almost everywhere to allow for the application of optimization algorithms such as gradient descent algorithm. Non-differentiable loss functions are not preferred. On the other hand, convexity helps in finding the global minimum more reliably during the training process. There are other factors also, such as the function must penalize the difference between the predicted and actual values more accurately. Scalability and computational efficiency are also important factors in this regard. So every algorithm that we see, whether logistic regression, artificial neural network, linear regression, they try to minimize some loss function, that is, they try to reduce the difference between the actual values and predicted values, and loss functions help in that regard. We have seen this hyperparameter learning rate many times now, especially in logistic regression and artificial neural networks. We represented them in the equations with the help of alpha. It is one of the most important hyperparameters of both the algorithms, and they decide the amount of change in the parameter values, or we also say the coefficient values, often referred as W in artificial neural network, and in logistic regression we represented them with the term B or BIs. So if we take learning rate as too high, then the training process might be unstable and the weights or coefficients could change, but so drastically that the algorithm overshoots the global minimum. On the other hand, if the learning rate taken is too low, very small, then the training process could be really slow and the algorithm might stuck in a local minimum. So coming up with the right values of learning rates is very essential for algorithms. In traditional machine learning, the commonly used range of learning rate is between 0.1 to 0.0001. Considering only 1 is not mandatory here, we can also consider values like 0.05, 0.07 and something of that sort. So we need to come up with the right value of learning rate before fixing its value in the algorithm, and it affects the training process a lot. Hidden layers, we discussed this concept in artificial neural network also. They are actually very important in a neural network architecture. The complexity of our data set allows different values of hidden layers. That is, if the data set is less complex, then neural architecture tends to have low number of hidden layers, but as the complexity increases, we usually have higher number of hidden layers. Moreover, the number of neurons in each hidden layer often falls between the size of input layer and the size of output layer. We gradually scale this network. We start from a minimal network actually initially, and then we gradually increase it until we get the desired performance. Finding the optimal configuration in this case is not straightforward. Once again, it is also an empirical process and it demands experimentation to maintain the balance between the complexity of the data to be taken care of and the complexity of neural network architecture. Then we also discuss earlier activation functions. Activation functions are really important hyperparameters once again in neural networks. While experimentation is important here also, often the hyperbolic tangent activation function is used commonly in hidden layers. It introduces non-linearity and enables the complex decision making. In contrast, the logistic function or the sigmoid function is common for binary classification tasks at the output layer because it gives you values only between 0 to 1. For regression problems, we use a linear activation function in the output layer for real value as an output. Each activation function has its own usage at the different parts of the neural network. It is also worth mentioning that a specific choice of activation function affects the performance of the neural networks. Now let's talk about what do we mean by hyperparameters. Parameters, this term we use often to represent the coefficients and weights internal to the model that are learned from the data during the training. They are not set manually. The examples include the weights in the neural network. They are called the parameters of the neural network. Hyperparameters, on the other hand, are the configuration external to the model that must be specified before the training. They affect the training process itself, such as learning rate, the number of hidden layers in the neural network, etc. Hyperparameters are crucial because they can significantly affect the performance of the model. Hyperparameter tuning is the process of finding the optimal set of hyperparameters for a machine learning model. It involves systematically testing different hyperparameter values to improve model performance, often using methods like grid search, random search, or more advanced Bayesian optimization. The goal of this tuning process is to enhance the model's ability to generalize well to unseen data so that the accuracy, the precision, or other performance matrices can be improved. There is another important concept called binary versus multi-class classification. What is the difference between these two? As the name suggests, in the case of binary classification, the dependent variable y has only two categories or classes. That's why the name binary. However, multi-class classification problems have more than two possible outcomes. It could be 3, it could be 4, or it can also be 10 or even more. We have used logistic regression so far. It is primarily used for binary classification. On the other hand, in neural networks, binary classification uses only one neuron with a sigmoid activation function, while neural networks also handle easily multi-class classification problems using multiple neurons which are equal to the number of the classes using a different activation function called softmax activation. So usually when we have multi-class classification problems, we tend towards artificial neural network and we prefer logistic regression often when the problem at hand is binary or is of binary classification. That is, it has only two classes to be taken care of. Moving forward, software activation is a special activation function used at the output layer of artificial neural network. What it does is it tries to assign a score to each possible class so that the sum of all the score adds up to 1. Once the scores are assigned, the class corresponding to the highest score is the predicted class. As I mentioned earlier, for multi-class classification, ANNs are the preferred choice. Now let's move to a very important topic called underfitting and overfitting. It is a phenomenon that takes place during the training process of any learning model. So what do we mean by underfitting? Underfitting refers to when the model we are considering, the learning model we are considering, is very simple. However, the data on which we are doing the training is more complex. So data is complex, the model we are considering is simpler to capture the complexity. As a result, we see that such a model performs bad even on training data. The other part of that is called overfitting. In the case of overfitting, the model considered is too complex and the data under consideration is relatively simple. And on training data, the performance is actually really good in the case of overfitting. However, when we try to generalize that on testing data, it performs bad on testing data set. So if your model is performing bad on training data, it might be an indication of that the model is suffering from the problem of underfitting, and we need to increase the complexity of the model. On the other hand, if the model performs good on training data but really bad on testing data, chances are the model is suffering from the problem of overfitting, and we need to reduce the complexity of the model. When we say reducing the complexity of the model, it might mean deleting a few hidden layers, or maybe decreasing the number of neurons in the hidden layers. Let's discuss these concepts further. So, what is the objective during the training process? If we consider this data set where the relationship between x1 and x2 seems to be linear, the objective is to identify the type of relationship between these two variables, and the desired relationship we want to identify is this line. But we might find ourselves in these two scenarios which are given flow. On the left side, you see the problem of underfitting, where our data is complex, but the model considered is relatively simple. In fact, it is the equation of a line, a constant line. On the other hand, you see the problem of overfitting, where we are not trying to identify the relationship between an x1 and x2, but we try to fit the data so hard so that there is no room for error. We can observe that in the case of overfitting, we are not trying to identify the relationship between the variables, but the focus is more on reducing the error that as a result of the function that we are fitting on this data. So, second one is an example of overfitting. We are going over in order to fit the data. Once again, this is the desired scenario where we just try to capture the basic relationship between the variables. Now, how these concepts manifest themselves in number? This first scenario here represents that when we come up with a model and the training accuracy is very low, it is an indication of that our model is suffering from the problem of underfitting, and maybe we need to increase the complexity of our model. In the second scenario, you can see here, our model is doing good actually on training data. It is not bad. But it is not doing good on the testing data. Chances are we are suffering from the problem of overfitting, and we need to consider a simpler model in order to gain a better performance even on testing data set. So what is happening in this specific scenario is that we are too busy in reducing the error in training. We are keep on increasing the complexity of the model, so we get less training error. But in the process, we are not capturing the relationship between variables on the dependent variable, but rather we are fitting whole data set in order to reduce the amount of the error, which leads to the overfitting. Once again, how we can see that? We can see that when we observe that the training accuracy is good, but the testing accuracy is bad. This is our desired scenario, where we have a decent training accuracy and also decent testing accuracy. This is the desired model that we are looking for. which does not only reduce error in the training dataset, but also generalize well to the testing dataset. So we should consider such a model. It is important to note that overfitting is very common in machine learning compared to underfitting. One of the ways to get rid of overfitting is called the concept of regularization. Regularization is an approach used to prevent overfitting by penalizing the models for their complexity. Thereby, it encourages simpler models that generalize better to unseen data. It works by adding a regularization term, we call it, to the loss function of the model that is used to train that specific model. There are many regularization techniques. The common ones are called L1 and L2 regularization. They penalize the absolute and squared magnitude of coefficients respectively. This regularization technique helps in enhancing the model's prediction accuracy on new unseen data by keeping the model's weights or coefficients as small as possible. Inbuilt libraries for supervised learning algorithms often provide the option to set the values of regularization terms. Now we have seen this concept of training and testing data many times now. Training data set, it helps us learn, it helps the model learn, which technically means that it helps us find the right coefficients, weights, or parameters. On the other hand, testing data set is used to check the performance of the trained algorithm, and there is an ideal condition associated with that. That is, your training data set might be available to the model that you are trying to learn many times, but ideally the testing data set should be available to the learned model only once. That is, the model should not see testing data again and again, because then there is a fear of fitting not only the training data set but also the testing data set. Let's see how, and it leads to the concept of validation set. Once again, our assumption in machine learning while testing on the testing data set is that the learning model actually should never see the testing data set. Now, what happens in real scenarios? Let's say I want to fit some model, let's say this specific function, which is a complex function by the way, and I get a very good training accuracy, but a really bad comparatively testing accuracy. As you can imagine, this is the scenario of overfitting. So as a result, we reduce the complexity of the function used and consider a relatively simpler model. When I consider this model, the training accuracy is still reasonably good. The testing accuracy improved, but not that much. Still, there is a problem of overfitting. I went further and considered a relatively simpler model. Once again, as you can see, a plus bx plus cx square. In this specific case, the accuracy of training dataset is once again decent. Testing dataset accuracy also increased, but not that much. Still, there is a problem of overfitting, and we need to further reduce the complexity of the model. Now, what is happening in the process is, by the way, it is a very real scenario. We often find ourselves in this situation where we need to supply the testing data set to the model. So this testing data set has been exposed to the model. Then once again, due to the bad performance of testing data set, we further reduce it. So the model or algorithm has seen the testing data set once again. We once again reduce it. Once again, our testing data has been exposed. And the assumption says that the algorithm model should never see the testing data except once when you are testing its performance on this unseen data. So what is happening in this specific case is the model is not only trying to fit the training data set, but it is also trying to fit the testing data set, because our testing data set is exposed to the model again and again and again. So how we can resolve that? For that, we use the concept of validation set. So as a result, the model learned testing data set as well. Validation data set is used to evaluate a learning model that has seen and fitted the training data set. It helps us decide based on the performance whether the learning model should be changed if the validation set performance is low, or the performance of the model, if it is fine, then it should further be tested on the testing data set. So this is what we do. Let's see the scenario once again before going into the detail of validation set. It represents the similar scenario as I have just discussed with you, where we start with the complex model, performance not good on testing data, reduce the complexity, increased the performance now. But here the difference is that we are not supplying the testing data, but we are supplying the validation set here. So what we do is we take our data set and we divide that into three categories. One is of course the training one, the training data set. Next is the validation data set, and the last one is the testing data set. The algorithm learns from training data set, tests the performance on validation data set, and test set is never shown to the algorithm or model except once when we have finalized our model. Let's see this. So we started with this complex model. We tested on validation set, its performance was not good. So we changed the model, we reduced the complexity. We considered a simpler model this time. And we supplied our validation data set once again, not the testing data set, validation data set once again. The performance improved, but is still not up to the mark. We further reduced the complexity and considered once again a simpler model. The performance on validation set increased, but not up to the mark once again. And then finally, we came up with this model here, which gives us a decent training dataset performance and a decent validation set performance. So even though during this process we learned, or the model or the algorithm learned from training dataset as well as validation dataset, but the final model, which is the 12th model in this case, a plus bx, has not seen our testing dataset. Once out of all these 12 models, we have finalized our model, which is the last one, then only we will bring up our testing data set, and testing data set is supplied only to F12, the final model. So if we compare that with the previous scenarios, previously we were supplying the testing data set to all these models. That's why it was exposed to every model. However, in this case, we use validation set instead in place of testing data set, and testing data set was reserved only to test the performance once we have finalized our model. So what we do is, when people try to use validation set, we divide our data set not in two categories as training and testing, but in three categories: training, validation, and testing data set. Training goes usually to learn the coefficients, to learn the parameters. Validation goes for testing the performance, and if it is not doing well, then coming up with a different model and testing once again on validation data set, and we use this process, empirical process, again and again. Finally, we brought our testing data set only once we have finalized our model. So when we do not use validation set, then often the distribution between testing and training is 80% and 20%. Sometimes we will also find 90% for training and 10% for testing. But when we use validation data set also, that very commonly we divide our data set, overall data set, into three categories: 60% for training usually, 20% for validation, and 20% for testing data set. Sometimes we will also find the distribution like 70%, 15% for validation, and 15% for testing. So to summarize today's lecture, we discuss what do we mean by hyperparameter, and tuning them is very essential to have a better performance of our learning model. We also discuss what is the difference between binary and multi-class classification and how neural networks are the preferred choice for multi-class classification problems. We also discuss the importance of validation set, and in many scenarios we divide our data set not in two different sets but three different sets: training, validation, and testing. Thank you.